Everyone. Thank you for joining us this evening. This is the EMBS Distinguished Lecturer event. This is our third event this semester. We have one coming up soon, so watch out for the flyers for that. We're very honored to have Dr. Chestek here tonight with us, and EMBS board has worked once again very hard to put this together. So I'm just going to pass on the floor to Haley, who's worked so hard on putting this event together. Please make sure you check us out, and the links will be provided in the chat, and join our student chapter. I'm the advisor for the student chapter. I don't know if I said that. And we'll have cool events coming up, throughout the year.
Yes. Let me share my screen. Hold on one sec. What is going on? Hold on. Everything good comes to those who wait, is what they say. Goodness. All right, there we go. So hi, everyone. Thank you for joining us here today. It's finally spring, so hopefully everyone's kind of enjoying the weather. It's getting a little bit better out there. So as Dr. Asmobehi mentioned, this is our 5th Distinguished Lecture event here at EMBS UIC. This is our 3rd this year. So our society is a neural engineering type society, but we also deal with every area really of bioengineering. Projects in the past have included InMove robot, BCI, and then wearable technology in general. This semester, given the pandemic, our current project series is called Making Waves, in which we deal with looking at EEG data in both MATLAB and Python. And then for those of you in the audience who are attending UIC, please make sure we're going to put some links in the chat so you can subscribe to our newsletter and then add our Google Calendar, which features both pop-up and recurring events such as Tea Time Thursday. And then a brief side note on Tea Time Thursday, for those of you interested, think of it as a space to talk about school, classes, remote learning struggles, really anything that anyone would want to talk about. It serves to provide a way to have that student-to-student connection, which has been harder to facilitate given remote learning conditions. So then today's lecture, Dr. Cynthia Chestek will be talking about neural interfaces for controlling finger movements. So thank you again, Dr. Chestek, for taking the time out of your busy schedule to be here with us today. For those of you who don't know, Dr. Chestek has received her bachelor's and master's in electrical engineering from Case Western Reserve University. She also holds a Ph.D. in electrical engineering from Stanford. She's currently an associate professor of biomedical engineering at the University of Michigan, where she's been a faculty member for, 9 years, since 2012? Yeah. And then there she runs the Cortical Neural Prosthetics Lab, which is both a part of the Biointerfaces Institute as well as the Multimodal Integrated Neural Technologies Hub. Her lab deals with brain and nerve control of finger movements, as well as high density carbon fiber electrode arrays. And then her research areas include implantable brain machine interfaces, systems neuroscience, upper extremity rehabilitation robotics, and then other assistive technologies. Really quick, before we begin, I just want to talk about a couple things really quick. So first and foremost, please hold all questions until the end of the lecture. We've set aside like 30 minutes or so for everyone to ask questions. If you're afraid that you're going to forget your question by chance, please feel free to just send it in the chat window and then someone will read your question later. Secondly, we also ask that everyone is, of course, respectful. So when the time comes to ask questions, please keep your microphones muted, although I think they should be muted anyways, but please don't test that out. And then lastly, as you can probably tell, this lecture is being recorded. So I'll be sending out a YouTube link to everyone who's registered in a couple days or so you can kind of access this lecture after the fact. I think that's all I wanted to talk about. So I'm going to stop sharing my screen, and then Dr. Chestek, you can begin whenever.
Sure
So can you see my slides? Okay. All right, so thank you so much for inviting me. I'm really excited about, in particular, giving a talk at UIC since my brother's in the audience and he's in the emergency medicine department. But very excited to be here. Sorry I couldn't visit Chicago in person, but very happy to talk to you guys. And so my talk is going to be about the neuroprosthetic control of finger movement. And I have the benefit of having some really excellent clinical collaborators at Michigan. So I'm on the engineering side, but I have these wonderful surgeon collaborators that I work with in neurosurgery and plastic surgery. And so my lab has what I think is a pretty unique privilege that we get to use signals from the brain, nerves, and muscles, all in the service of trying to control hand movements. So we're thinking about this in terms of different medical applications. So when we're thinking about using nerves and muscle signals, we're thinking about controlling a prosthetic hand for someone who has suffered an amputation. Whereas if we're thinking about brain signals, then we're typically thinking about spinal cord injury and eventually trying to use these signals to stimulate paralyzed limbs. So, functional electrical stimulation would be the ultimate output. So in my talk today, I'm going to start with nerves, which is the thing that's actually happening in people right now. So that's our clinical trial. And then I'm going to go sort of, one step back from in people. And then I'm going to end with sort of the most science fiction-y thing that my lab works on, which is our carbon fiber electrodes, which are all smaller than the neurons themselves. So let's start with nerve-controlled prosthetic hands. So Empire Strikes Back came out in 1980, which is 40 years ago. And the idea of just, taking a hand and controlling it with nerve signals is much older than that, probably in science fiction. So why have all these very smart, very hardworking people been working on this problem and we still don't have a nerve-controlled prosthetic hand? And the problem, I think, is that the physics just isn't in your favor if you're trying to get the signal directly from the nerves, right? You're talking about an extremely small, extremely well-insulated little wire, and you're trying to get the signal out. And if you start stuffing wires into the nerve to get closer to that signal source, the nerve's going to be very unhappy about that. So this, outside of sort of these controlled laboratory demonstrations, nerve-controlled prosthetic hands is very, very difficult. In fact, it's so difficult to get any real measurable signal from a nerve that it was easier for my plastic surgery collaborators, and particularly Paul Sederna, to take a nerve and turn it into a muscle instead. So, and I know this is very similar to targeted muscle reinnervation, but there's a couple of very key differences. So, the idea here is you take a amputated nerve, you divide it down into smaller branches as necessary to get, about the right size branch. And then you take a small piece of muscle from the same person and you wrap that around the nerve. And if you get the size just right, it doesn't die and the nerve reinnervates that piece of muscle. And so now you have created a new muscle where before you only had a nerve. And I know, targeted muscle reinnervation is very big in Chicago. Probably the biggest difference is that you don't have to reroute any nerves and you don't take a pair of scissors to any healthy nerves, right? So this can be done in place. And in fact, this has been done, over 500 times already at the University of Michigan. So we call this the regenerative peripheral nerve interface. But you can also, if you can just remember like a muscle burrito that we're making with the muscle and the nerves, that is what we're doing. And this was able to progress. So we did, our colleagues did a lot of rat experiments. In my lab, we did this first in non-human primates. And then we were able to go very quickly to humans because this turns out to be an excellent treatment for pain. Right? So these nerves can be very painful if they're not terminated by anything. And so that's why it's been in so many people. And then we were able to go and work with that same population for using these small muscle grafts for prosthetic control. So So sorry, gory surgery picture. Should have warned you, but this is EMBS. And so this is what the surgery looks like. And so this person received 10 actually of these muscle grafts on different nerves that were divided down into different branches. So this looks pretty dramatic, but you can notice the scale bar here. These are very small pieces of muscle. And in this person in particular, this was done well above the elbow, where the finger muscles are gone. So we're talking about like the bicep, tricep area. And so we would not be able to get these signals from existing finger muscles. And the easiest way to see what we did, I think, is under ultrasound. And so let me play you some ultrasound videos. But first, let me say that this particular person had an amputation over 15 years ago. And he said he felt like his hand was completely frozen and he couldn't move it. And then after the surgery and the months that followed, he said he could feel his fingers give, right? And so he didn't have full range of motion by any means, but he could suddenly felt like he could wiggle his fingers. And if we look under ultrasound as to what's happening, I hope my movies play, this is in the tricep area, but we've asked him to flex his thumb. And you can see right over here, there's a small wiggling thumb muscle now in the tricep area. And similarly, if we go over to the ulnar nerve, one of the things we expect anatomically is small finger flexion. And indeed, we see another little muscle that is flexing when he attempts to move his small finger. For a control, we asked him for movements that we wouldn't expect to see on that nerve. So on the median nerve, we asked for a small finger. You can see it happening off screen from the other graft, but this is staying still. And then the ulnar nerve does a lot of things, but middle finger is not well represented. So that's our control movement there. And you can see we don't really see movement when he's moving his middle finger there. Okay, so after that, after we did sort of a series of experiments with people who got the surgery for other reasons, we went to the FDA and we got permission to temporarily implant electrodes. And these are electrodes that are designed for diaphragm pacing, and they are meant to go through the skin for long periods of time. So one more surgery picture, and then I promise we're done. But we're very grateful to our 2 study participants so far that have volunteered to get these connectors on their arm. And these go to very small wires that are inside of the grafts. So they can come into the lab, we hook up to these connectors, and they can start controlling the prosthetic hand. So now let me show you some of the muscle signals that we record on these grafts. So this is from our first participant that got the electrodes implanted. And so the first thing you can see here is, so my EMG signals are here and they're deflecting from that line in the middle. And the signal to noise ratio is big. Like these are big signals compared to what we would get if we recorded from a nerve. The signal to noise ratio is in the range from 30 to 150. For comparison, if I was trying to get a signal from a nerve, I might be happy with the signal to noise ratio of 2. If they're just very, very small signals. So the other thing you can notice here is that they're very specific to the movement. So across here, we have, thumb, index, ring, and small fingers. The ulnar nerve, as you would expect, likes thumb and ring and small fingers. It's a slightly different set of thumb movements. And the median RPNI loves thumb movements. And you can see how ridiculously specific it is to thumb movement. So this is a good prosthetic control signal that's going to tell us a lot about which movement they intend to make. All right, so first let me start with something really hard. We're going to try to classify from these voltage signals. And I should say, we also implant electrodes in whatever residual muscles they have. So a lot of the thumb muscles are in your hand, so we get a lot of that from the RPNIs. But in this case, this is a transradial amputee, so there are other muscles, and we also stuck some electrodes in those muscles too. So this is what we can do with everything together. And I'll show you a video later of what we can do mostly with the graphs. So now we're trying to classify 10 different movements. And you can see, we're doing it on the left offline. Perfect score is all yellow on the diagonal. Over here, we're 98 and 97% correct. That's, offline, like looking at the data after the fact. Online, when they're controlling an animated hand, we're at about 92% and 86%. And that's all 5 fingers, abduction, adduction. The thumb is broken into 2 different movements, and we have wrist. So that's a lot of different movements we can classify. And the latency is on the order of 160 milliseconds for one participant, and our slightly slower participant is at 297 milliseconds. And the algorithm here is a hidden Markov model to make the classifier work a little better. So let me show you a video of what this looks like. So we are controlling the hand in front, and this is actually the slower, our 2 participants. And she's controlling the hand in back. So I hope my movies are coming through so you can see that it's pretty zippy, right? Like she sees it and, she can make the same movement. There's a few mistakes in there, but again, this is 1 of 10 different movements. So pretty good. And you can tell this is going really fast because it's an animation. That was a hand splay. And again, we're also doing movements here that we can't even do with our prosthetic hand. So like finger abduction, adduction. This is a video of doing our other participant doing this with the DECA hand, which is pretty fast, right? So this one, you can see it can't make all of the movements, but it can switch very quickly between them. So these are the, a fist, pinch, and a point, because these 3 fingers are locked together. And the trick here is that this is working in multiple postures, which took a little bit of doing, but basically these signals are very strong, and if you train in a wide variety of conditions, you can get pretty good control in multiple postures. Let me play one more video. So that was the DECA hand. Now I'll say the DECA hand is a wonder of engineering, but is extremely heavy. Right, so it's not really very realistic to use in daily life. So our next participant, it was too heavy. So we're using a really state-of-the-art clinical hand, which is being provided by OSER. And you see here, she's going to control all 5 fingers. So she'll do it correctly sitting, correctly standing, and then she'll make 1 mistake when she's holding her hands up here. So she can do all 5 fingers. But you can see here it's moving a lot slower. So, and that's just, that's the necessity of, the weight is definitely related to the speed. And because this is a realistic weight, it's a lot slower. And that does currently make it harder to do continuous control. So because it can't quite move as fast as you can move it. But, we're hoping that having access to better nerve signals is really going to motivate faster and more capable prosthetic hands. All right. We are very interested in more than classification. And so we want to get continuous control over these joints. So, moment by moment control of the position and velocity. I think this is a video of the first time we tried it, I believe. Yep. So this is week 1 after surgery. I had just said, this might not work on the first try. You've got to bear with us if we need to do some debugging. And he said, well, it seems to be working. And this was, so starting out, this is just a simple 1 degree of freedom thumb controller. We still haven't published this in a paper, but in general, we don't recalibrate, right? So we come in and, we don't need new calibration data. We can use parameters that we trained in a previous session, though we still have to rigorously show that in a publication. And so here, let me play you another video of continuous control, which again is using the DECA hand because it's much faster. And this video is an example of something that we couldn't have done without these muscle graphs. Because when you think about it, a lot of the muscles that control your thumb, if you wiggle your thumb around, are actually in your hand. And so using these muscle graphs, we're able to get a pretty good 2 degree of freedom thumb controller. So my student is holding a target over here on the right, and our participant is controlling the hands. So you can watch, he moves the target around in the thumb's range of movement. And this is being driven primarily by these muscle graphs. which give us those very strong thumb signals.
Down, up,
Now let me play one more video with continuous control of the thumb and the index finger, though the index finger isn't coming from the grafts, it's coming from his existing muscle. Oh, sorry. Yeah, no, I think it's in here. Yes. Okay. And there'll be a little bit of another task. So watch his thumb here. So he's picking up blocks. Then he needs to get blocks out of the corner, so he moves his thumb out of the way. And I think this is sort of the most functional mode that we can give our participants, because when you think about it, if you start reaching for objects on the table, if you can't orient your thumb, it is really hard to pick something up. And so just being able to orient your thumb around objects alone is pretty helpful by itself. And this is our other participant. So it's a little bit slower, but she can still switch intuitively between these multiple grasps. And you can see this is continuous control. So she makes a mistake, but she doesn't have to make the whole mistake. She can stop halfway and reopen it because it's in a continuous control mode. All right. So I normally pause for questions here, but I know we're holding them towards the end. I'm now going to switch gears from nerves into brain. So this is, not quite ready for prime time, but when I started my monkey lab, we were thinking about, okay, well, what's sort of the next thing? And I think the state of the art around the time that I started my lab was monkeys with Utah rays, and Utah ray is a small bed of needles that is implanted in motor cortex. So this looks really dramatic, but it's about, yay big, it's 4 millimeters across. And this is about the state of the art for trying to control a computer cursor using one of these Utah rays. So this is a monkey at Stanford. So I have to say probably a little faster than EEG, right? And if you have a monkey typing, you have to have him type Shakespeare. So let me pause that. It's a little bit loud. So note, the monkey can't see the letters, he's just seeing the green dot. So he's moving the white dot on top of the green dot. So the monkey is not composing, but it's cursor control is a fairly solved problem. Like there's obviously, you have to translate this to humans, that takes a while, and there's, difficulties along the way, but 2 dimensions is, pretty straightforward at this point. So at least as far as controlling endpoints. But if you can only control the endpoint of your hand, you can't make the hand do something useful. So in my lab, we chose to focus on finger movements, and we're trying to get to eventually, as many degrees of freedom of the hand as we can. One more surgery picture. This is what the Utah ray looks like in the brain. It's very small. Okay, so what is the state of the art here? So I would call the state of the art, there was a landmark study from Case Western where they, using exactly those same implants, they were able to give someone with a cervical level spinal cord injury control over a few degrees of freedom of the arm. So, so you can see here, there's connectors on this person's head, and there's actually functional electrical stimulation leads going into his arm. And so, and he was able to use this to pick up and grasp a fork. He was able to use this to drink coffee. And even, I know we said we want to get multi-degree of freedom, but this is already something that we really wish we could send somebody home with, right? There's very few treatments for cervical level spinal cord injury. This thing on the right here, by the way, is just a gravity support. So he was in control of those movements. All right, so first question I always get at a conference, why don't we make it wireless, right? Like it's been a really long time, why don't we just make it wireless? And the problem is with how we do this, right? So this person has 200 wires coming through the skin on his head. He has 32 wires going back through the skin on his arm. And that that we're actually processing 50 megabits worth of data if we do this sort of, the old-fashioned way and how we process these signals. There's just too much information trying to come through, and there's no such thing as a pacemaker, with realistic power consumption, like an implantable device that could process 50 megabits per second worth of data. So if you presume you need this architecture, it's impossible, right? Like it cannot be done with circuits as we know it. Okay, so in my lab, and in particular my student, Sam Nason, we thought really hard about how to get this power consumption down. So what do we actually want from this signal? When I put an electrode near a neuron in the brain, what you get is these little check marks. And so it's a deflection in voltage, usually bipolar, that happens every time that neuron fires a spike. And if a neuron is close to the electrode, it's going to fire a big spike. And as it goes further out, the size of those spikes drop off as you move away. So all I want is the spike, and I want the firing rate, that's actually like how many of those spikes did I get? So okay, so what do we actually have there? So if we take the Fourier transform of that spike, so if we represent that spike according to its frequency components, we get the curve down here. And you can actually see, this is about like a 1 millisecond sine wave, right? So it has a lot of power right around 1 kilohertz. And so, if we filter this signal between 300 and 1,000 hertz, we get a lot of information about the firing rate. And I would say, we're not the first to notice this. It was noticed in, I think, 2007 with Stark and Abeles, where they said, this high frequency band is really suspiciously good, right? Like we can get a lot of information out of that band. And then, in Sam's paper and simulations, we showed, yeah, that's because it's the spikes, right? And so if you look at this, if you have your true firing rate of the neuron, so you have a neuron here that's spiking, and this is the raw voltage trace in black below. If I take the average, between average power between 300 and 1,000 hertz, I get these blips down here, right? So, and then if I take the average of this across a longer time scale, I'm going to get the average firing rate. Okay, so that's how it works with one neuron. Of course, you might know that if I put an electrode in the brain, I'm going to get a lot of neurons. And this is where I think we were really surprised, right? Where it turns out that compared to the way we normally do this, where we would sort of put down a threshold and detect whatever crossed that threshold, this actually works better than that. And it works better at lower signal to noise ratios. So what you're seeing here now is a signal that maybe looks more typical of a brain electrode, which is a mess. Like there's neurons in there, but they might have very low signal to noise ratios. And so you can see here on this graph, as we're going down and left on this plot, we're going towards lower signal to noise ratios and lower firing rates. And you can see up top here, I have threshold crossings, which is how you normally find these spikes. And down here, I have this 300 to 1,000 hertz band. And you can see it's going much, much further to the left. And here you can see, if my true firing rate is in green right here, threshold crossings have no idea what's going on, like cannot detect the spikes. But you can actually, if you squint, you can make out the firing rate of these neurons in the spiking band power. And this is super cool because how often do you dramatically simplify a system? And I'll show you in a second, this is 90% less power consumption. And it actually works better, right? And there's some cases where it'll work as well, but it's always as well or better. Okay. So before I show you this working, let's talk a little bit about algorithms. So how do we actually interpret this brain activity? So there was this really cool paper that it was a privilege to be a part of back in 2002 that developed an algorithm called the refit Kalman filter. So if you were a monkey in a BMI lab prior to about 2009, you can maybe do this task just fine with your real arm, which is the graph on the left. But on the right, that is a what's called a Kalman filter, which is, by itself, it's not very good, right? So this is a monkey. You can see he usually misses the target and has to make lots of corrective movements. The refit Kalman filter is a very small modification of that. And the idea is you have to basically do a better regression, right? So you use regression to train this. In the refit Kalman filter, there's a refit step where you go online, you go through and you sort of fix up your training data. And every time the monkey was not moving towards the target, you say, no, he meant to be moving towards the target. So you just change it in the training data, you do a new regression, and then you go back and it's just a regular Kalman filter primarily. And you get the graph in the middle. So now this is working a lot better, and you can see it looks a lot more like the graph of the native arm. So in my lab, what we wanted to do is extend this technique and extend this control, from endpoint to finger movements. So first we did that in 1 degree of freedom movements. So you can see this is our monkey's task, where he's moving a little manipulandum. And as far as he knows, he knows how to do this task with his fingers, and he only ever sees the animated monkey hand on the left here. So you can see the cartoon monkey hand, hopefully. I don't know if that's coming through. Well, monkey hand over here. And what I just showed you was brain control, right? So that was a monkey controlling this cursor with brain activity entirely. So that's 1 degree of freedom. And the refit Kalman filter does seem to also work pretty well in fingers. So let it play again. Now that's actually going. So it's doing pretty well. That was a few years ago at this point. So now, can I get you guys to just pause the video for just a second here?
Sure.
Cool. Okay. And so this is just a graph showing, so yes, what you just saw was done with spiking band power, which means 10 times less data and 10 times lower power consumption, right? If you did that in an implantable device. And this is just showing you on the left and the right, you shouldn't see any difference. This is the traces of the monkey's finger, and the green is the target. And, we can do it both ways, right? And it works really well. We actually did, both an experiment, and then we did a simulation of an integrated circuit to say, okay, well, what does it mean if we can do it in this much simplified way? And we measured in both cases, a 90% power reduction. And it's because we don't need to mess around with high frequencies. We don't need to be able to see those spikes. All we need is that very low frequency, 300 to 1,000 hertz signal in order to, reproduce any BMI video you've ever seen, as far as we can tell. Okay, so that was, that is something that, it's not in humans yet, but we think it's very close, right? Hand FES systems already exist. The Utah array already exists, or is already being used in people. So we're very motivated to, try to add that capability to functional electrical stimulation systems. Now let me go one step further back, and let's talk about, how do we make both of these things much better? Because, what you just saw, particularly in the human experiments, those are our human electrodes, clinically available. The Utah array has been used in humans for, well over a decade. But, if we want to do substantially better than what you just saw, we need a lot more channels, right? Like if I want to do all the degrees of freedom of the hand, imagine, I'm quite sure I need at least 1,000 channels, right? So why can't I do that right now? I can't do that right now because if you put any kind of conventional electrode in the brain, it's going to cause a big scar, right? And so you can see here, this is from Pat Tresco's lab. Orange over here, it's kind of hiding, is where the electrode was. And blue dots over here are neurons. And you can see there's missing blue dots and a substantial amount of missing blue dots near the electrode. And that extends about 150 microns from that electrode. In fact, I kind of have to go all the way out here to 400 microns to find more healthy neurons, right? And that is maybe not coincidentally the pitch of the Utah array, right? So, I can't just keep putting those tines closer and closer together. There is a significant problem with scarring. Even if you're sort of assuming, if you're doing this over a long time period, like it's not going to be something where you can keep sort of increasing the density. So a solution for this started appearing in the literature, I think, with John Seymour's paper in 2007. And then also, they were working on something very similar in Pat Tresco's lab. And what these were they started making these lattice probes, and the elements along this lattice were smaller than neurons, right? They ranged from 4 to 15 microns. And if you count neurons around, these very small elements versus around like, for example, the solid shank electrode as a control, you'll find that, the neurons around these small elements are 85% of normal, right? So that kind of suggests that if you make your electrode small enough, it can fly below the radar of the immune system. So this was really cool. However, I don't want to, we don't want to do it like this, because if you put one of these lattice structures in the brain, you're going to, you're ripping up synapses and neurons like as you go in, and then you're kind of waiting for it to heal, but it's still not a way that, you want to safely get 1,000 channels. So what we somehow need is an electrode material that we can make smaller than a neuron and still somehow get it into the brain. And again, 15 microns is closer to the size of a cobweb than it is to the size of a hair, right? So you're talking about something really, really small. And so my lab and others do this with one of the strongest materials that we have available to us as engineers, and that's carbon fiber. Right? So we found this in a textbook, but it's a really good summary of all of the things that carbon fiber can do that a lot of other materials do not have. So high tensile strength and modulus, good fatigue resistance. I can bend it back and forth. Actually, let me play that video. This is a glass capillary running over carbon fibers. That they do have to be in something soft so you don't violate their radius of curvature. They're electrically conductive, they are chemically stable, excellent resistance to acids and many solvents. And actually that's really important for the brain, because you end up with materials failures if you put something in the body for long time periods. It's also, so, it's basically very strong and very cheap. And so, you can make a pretty darn good, very small electrode using carbon fiber. So carbon fiber, it was used in neuroscience for, a very long time as a chemical sensor. And there they would sort of put it inside a glass capillary. T.K. Kozai was the first to develop a sort of singulated carbon fiber electrode that could be individually placed in the brain. And we still use a lot of those methods today. So we start with a bare carbon fiber. You have to coat it with something that's insulating, like Parylene C, and that we still use. You have to cut the tip, which we now do in a wide variety of different ways to get, different properties, shapes, etc. We use lasers, blowtorches. You can get a lot of different properties. And we're actually moving away from PDOT, but you need some kind of conductive coating on there. We're actually switching over from PDOT to platinum because we think it lasts a little better. So my lab was the first to put this into an array of individual elements where, all of the elements were, smaller than a neuron. And so this is work by Paras Patel. And so this is the video. So it took a long time to figure out sort of the critical buckling dimensions and how to get this to work. But what you can see here is a 3x8 array, and those carbon fibers are just disappearing past the surface of the brain. Right? So, you don't even really see much of a reaction at these if they're this distance apart. Nowadays we're putting them more like 80 microns together, but it's 8 microns, much smaller than a neuron, and it can be driven directly into the brain. So what you're actually seeing back here is it needs a little bit of help with gradually widening silicon. So that's one of the ways that we can get it, the whole millimeter down to motor cortex, for example. Okay, and indeed, after the fact, if we then, and this is all done in rats, if we go back into the brain and image the neurons, and this is 11 weeks after implant, and here we have traced out the line of the carbon fibers, you can see that, even many weeks after implant, when you would expect the scarring to set in, that these neurons are really up close and personal with the electrodes, right? So in more recent data, they're about, the closest neurons about 15 microns away from the carbon fiber, and that's after a long-term implant. So here's another still image of this. So you can see down here, this is control brain. So that's what healthy brain looks like. And each of these green blobs is a neuron. Up top, this is a ray that had carbon fibers in it for 13 weeks. And there's actually no significant difference between the number of neurons in the top image and the bottom image. You can see there's a little bit of, red in there, and that is there is slightly more inflammation near the electrodes. But in general, this is pretty good. And, we estimate that, this will end up with a lot, many, many more of the neurons being spared under the electrodes compared to, for example, a Utah array. All right, and we're also really hoping, because it appears that we can find the tip of these electrodes, that we're going to be able to actually reconcile, the neurons in this image with the action potentials we recorded. So that's what we're working on right now. And I also want to point out, so particularly with a lot of the, conventional electrodes, it's not just, the number of electrodes you have. There's some really high channel count electrode systems. They are very cool, but it's not just about channel count, it's about quality, right? And if you have, if you put in an electrode with 1,000 channels on it, but only a third of them record something, due to damage and other reasons, that's bad. With carbon fibers, my student Alyssa Welly just published that we have extremely high yield, right? So the yield is, almost perfect immediately after you put it in, and that's about 80%, maintaining units or, neural recordings after a chronic implant. So, we're much more likely to have a neuron on a carbon fiber, for example, compared to a silicon electrode. They're also very small. So for example, I know I told you it was really, really hard to put wires inside of nerves. This electrode is really, really small. So we're doing this, for example, in rat vagus nerve, which is, maybe 300 or 400 microns. And this is work by my colleagues, Tim Bruns and Ahmad Jaman. And so you can see we're getting pretty decent single units. So these are spikes that were recorded from a vagus nerve using a carbon fiber. And it's kind of cool. You can actually, in some cases, see the action potential travel along that array. So right now we're in the process of distributing a large number of devices. Haley mentioned the Mint Hub, which is, we're very grateful to be funded by the Brain Initiative to distribute these devices. We can put, we have a bunch of different lengths because we work with a lot of different groups. We can put them on any number of connectors. You can still use carbon fibers the old-fashioned way, which is to do dopamine sensing. So we can make our electrodes so that you can do that with them. And right now, so if you're interested in getting carbon fiber electrodes, if you Google like Michigan NeuroNext or NeuroNext Mint, at least for the next year or so, we're distributing these devices, and I think we're actually over 400 devices at this point to over 30 schools, and there's one international in the United Kingdom. So, all right, so. Let me sort of end by saying, we're not the only game in town for super small electrodes. And if I was getting into the field right now, I would be super, super excited because this whole thing where we can make a wire live in harmony with the immune system is brand new, right? So when I got into this in 2005, brain-machine interfaces were a pretty cool trick, but we had no way of, dealing with the scarring problem. I think we were just sort of hoping that a solution would come along. Now, we have the Net Pros from Changji's lab, the Neuralace Pros from the Libra lab, Nick Malash's lab also has very, very small electrodes. And reliably, we're seeing the same thing. Wires can live in harmony with the immune system. And so again, if you look at the dates on these, they're all very much within the past 5 years or so. And obviously, it's going to take some time for this to make its way out to medical settings, but it's going to get there, right? And this is much, much safer than doing things with conventional electrodes, which I think in turn is going to unlock using neural interfaces for a lot more medical applications. So again, I'd be really excited about this if I was, just starting out in this field. So with that, I want to thank my funding sources. These are chronological in terms of, the sort of 3 areas of my lab. And I also need to thank my lab who has really stuck it out this year in Zoom. This was one of our first all Zoom lab meetings after we had sort of shut everything down and like gotten the last bit of data as everything's shutting down in March. But yeah, so definitely thanks to all the people that actually did all of the work that I get to sit up here and present. So with that, I'd be happy to take any questions.
Wonderful. Thank you for this talk. There's so much that like I don't know that I'm gonna have to go research now later.
Sure.
If anyone has a question, they can raise their hand and then you can ask it. Otherwise, I do have a question in the chat that I can ask, which in fact, I will do that first. So someone asks, in the human study, is it possible to use EMG amplitude or frequency components to control force or speed? Also, did you try any nerve stimulation to get sensory feedback?
So, yeah. Okay. So, yes, and I think our actual feature is mean absolute value. So we're using like, mean absolute value. We primarily decode to velocity. Right, so we're kinematically we're trying to get a velocity output, but we sometimes do position and velocity, and we have not done force, but there's every reason to suggest that, or every reason to think that we could probably get force signals out of this also. On the sensory question, yes, we have stimulated, and we've even done a little bit of like hard soft discrimination. I think this is, you can absolutely stimulate on these electrodes and use that as a sensory signal. That said, we still have the problems that, the whole field has trying to get naturalistic sensation. It does feel more like a buzzing. There's obviously excellent work in Chicago in this area from Sleeman Ben Smaya, but, we have not yet gotten a naturalistic sensation. Also, our signal amplitudes are higher than if you were actually in or on the nerve. So, we can do the same things, but at a slightly higher current amplitude because we're not directly touching the nerve.
Does anyone else have any questions?
A couple, if no one else does. I couldn't find the hand raise button. So I'm sorry to just jump in there. But at the very beginning, when we were talking about regenerative peripheral nerve interfaces, I know you mentioned pain control and pain treatment. So I was wondering what pain specifically, and if you had any research for maybe phantom limb pain and using that as potential treatment.
So I'm the other members of my team are much more the experts on pain. So I'm gonna try not to butcher this. Certainly neuroma pain, right? So the part of phantom limb pain that is neuroma pain, this basically fixes that, right? You can sort of show afterwards that, the neuromas have been resolved. To my understanding, phantom limb pain can be a lot more than that, can involve, central components and things like that. And so, we're not saying this can cure all of that. But I think that, for example, at University of Michigan, they're trying to do these prophylactically, right? Sort of under the assumption that if that pain never develops, right, then maybe you can prevent it from the outset. And, if you always feel like you can move your fingers, then, you'd think this would be really effective for preventing phantom limb pain. And that is the topic of like an ongoing clinical trial that is sort of running parallel to this prosthetic stuff.
Awesome, thank you. And I had one more question. For your monkeys typing Shakespeare, how did you choose the order of the letters?
So that was my the lab I got my Ph.D. in with Krishna Shenoy at Stanford. The monkey just saw the green dot. So if you just remove all the letters, one of those dots was turning green, and his job is to put the white dot on top of the green dot. So, and then just the ordering of it was such that it would spell out Shakespeare.
Oh.
So the monkey was not composing.
Okay, I thought it was like, I don't know, I thought maybe it's like if this was a human trial, like the most efficient order of letters for this system.
No, but I mean, I think that, I show that because I think a lot of people haven't seen the really good BMI videos, and like it's gotten pretty good. Like that's a hard act to beat for just two-dimensional cursor control. So we have to definitely think about more degrees of freedom.
Awesome. Thank you so much.
Sure thing.
Heba has a question, so Heba, you can go ahead.
Thank you. First of all, I'm really glad that you had all those videos in your talk. I think I personally haven't seen, like, as you mentioned, great BMI videos, so I really appreciated those.
Sure.
But for the first part of your talk with the finger movements, I was wondering if you tried measuring signals from any other muscle regions, and like why specifically you chose the muscles you did for decoding certain fingers movements.
So when we plan out these surgeries, we have a certain number of wires that we can put in, right? And so we certainly, like, the primary goal of our study is to study whether these muscle graphs are giving us good signals. But whatever channels we have left over, we sort of plan out what is best for that person, right? So in the case of somebody who has a transhumeral amputation, we're mostly going to be putting those in, the muscle graphs. In the case of somebody who has a more distal amputation, we're going to use these graphs to get that good 2 degree of freedom thumb movement. But, there's going to be like an index finger muscle in there. There's a bunch of other muscles that we can access, wrist control, things like that. And we plan that out on a per person basis. So we just did it for, a surgery that's coming up, hopefully in a few weeks. So. But it's a very individual, we have a certain number of wires, and we want to deploy those wires in a way that gives that person the best control.
And then, sorry, I have a quick follow-up question. Is that okay, Haley? All right. So like you said, this is a bit more of like a person-to-person basis. Is there anything that that you guys could do to make it more generalized at all?
Well, so I mean, I think that this surgery is very generalizable. So for example, like in normal practice, a prosthetist has to take whatever they get, right? Like whatever signals are available, that's what they got. They do the best they can. Whereas with this surgery, whatever's missing should theoretically be on the grafts, right? So, and you can divide down the nerve into different branches. And so one of the things we're hoping for, from sort of a medical realism perspective, is that this is going to make people with amputations more uniform in terms of the signals they have available, if that makes sense. Like, you can kind of always hopefully count on that thumb signal being there. The other thing is we're hoping this will be much easier for the prosthetist, because by the time this is an implantable device, everyone's the same. They can make the socket not based on where these muscles are, but, make the most, comfortable socket, and then a little antenna gets the signals out. Right. And so I think that, I think that in 10 years, prosthetics will look like that.
Thank you so much.
Sure.
Any other questions from anyone else?
I have a question if there are no other questions.
Sure.
This is a great talk. Thank you. I learned so much. I'm just curious, what is your thought on Elon Musk's Neuralink, and how do you think that will have an effect?
Yeah, I sort of count like how long it takes for somebody to ask me about Elon Musk at this point whenever I meet new people. I think it's fine, right? So like, I think, for example, Heba mentioned that, like, you don't see a lot of these movies, right? And I think it's because scientists aren't doing a great job sort of showing like how well this stuff is working. So I'm really hoping that, like, the community and the people will discover how well the stuff is already working, right? That we do have paths to, thousands of channels that might just require like the addition of money, right? So I'm actually really optimistic about this, right? I do not think it's going to happen in able-bodied people. So that, like, not going to be a thing, at least, for decades and decades. But, as far as the realism, right, of doing this for real and having this as a sort of in the arsenal of medical treatments, yeah, I think it's absolutely time to do it. It might be slightly early, but it's only slightly early.
Thank you.
Sure.
Any remaining questions? Don't be shy. No?
All right.
Yep, I think that's it. Well, thank you again, Dr. Chestek. This was a great lecture. So I'll send out a link to everyone with the YouTube link whenever that gets processed. It takes a little bit, and I'll include you in that as well. So thank you everyone for attending. Thanks to IEEE EMBS for making this possible, and I hope everyone has a good rest of their day.